Hi everybody, my name is Tanielian. Today I'll present our work on Relaxed Softmax for learning from positive and unlabeled data. This work has been done with Flavian Vasile at Creator Research. So, in recent years, Softmax has become the de facto loss when tackling multi-class classification problem. And this loss has been extended to recommendation and language problems. Even though these two fields fall into the framework of positive and unlabeled data learning. In this paper, we define a new objective called Relaxed Softmax, inspired from PE learning. So what is our problem? Both in recommendation and NLP, we only have access to ground truth data. Indeed, in NLP, we have access to sequences of words in sentences or documents, whereas in recommendation, we only have sequences of users clicking on ads, users watching movies, or users listening to different musics. And in both cases, what we want is to learn conditional distributions. For example, what is the likelihood of user watching movie B, knowing that he has already seen movie A? Okay. So now we put ourselves into the framework of PE learning, positive and unlabeled data learning. It has been defined in 2005 and can be considered as a two-class classification problem, where one only has access to positive data. And a classical technique in PE learning is to define a set of reliable negatives, either using a classifier or a prior distribution, and then we move back the problem to supervised learning by defining a discriminative loss that separates the true positives from the artificially created negative data. And that's what we'll do for our problem. So now a few notations. So we consider either I and J the context and target item spaces. We also consider P and Pi the true distribution and the conditional true distribution. And P hat the empirical distribution, as we only have access to finite samples. And so our model to model the conditional probabilities would be a really deep neural network. So we use the Waterlake architecture. And at this time, we have to keep in mind that to compute our likelihoods, we use the softmax function. Okay? So a straightforward training loss would be to perform maximum likelihood estimation using the softmax function. And this loss comes to actually maximizing the likelihood of pairs sampled from the true distribution, P, and minimizing the scores of all the other potential candidates. But actually this loss comes with many drawbacks. Indeed, softmax is quite expensive to compute, and it requires to backpropagate the gradient to all the parameters of the model. Second, softmax is a density estimation technique, as we are minimizing the head divergence between the empirical P hat and the model distribution. And therefore, it might not be performant on ranking metrics, such as precision at K or MTR and so on, that we use in recommendation. And that is why we argue in the paper that negative sampling schemes should not try to approximate softmax, as the noise contrastive estimation or sample softmax are doing, but on the other hand, they should be discriminative losses, as for example the negative sampling loss used by Nikolov and al in the Waterlake architecture. But also a problem of the previous sampling schemes is that they were focusing too much on context-independent sampling distributions, such as the uniform and popularity-based distributions. And these sampling schemes are making too simple assumptions on the shape of negatives, and therefore they might return non-informative items. And for example, one of the problems that was brought up by Chen et al. In 2017 is that when the model gets better and better, these negatives, they move away from the decision boundary, and therefore the gradient becomes the magnitude of the gradients become too small, and therefore they become really uninformative. And consequently, to counter all these drawbacks, we propose in the paper, first, a contextual sampling scheme that can handle the high diversity of conditional distributions in both recommendation and language. We also propose dynamical sampling that will evolve with the model, and therefore we will return informative negatives throughout the whole training. And also we propose a discriminative loss that will separate positive data and wisely chosen negative data. And we show improvements over classical methods. And so how do we do it? We actually over-parameterize the negative sampling distribution by using a Boltzmann formulation. Indeed, we define a new Boltzmann sampling scheme that is a function of three things: an energy state, GI theta, that accounts for the estimated likelihood, a distribution QI, responsible for the negativity of the target item J, and a temperature parameter that has to do the trade-off between the two. Indeed, when we look at the distribution BI and we look at what it converges to when T converges to 0, we see that BI converges to a Dirac centered on the most likely item. On the other hand, when T converges to infinity, BI converges to QI. And here we can see really the two behaviors. With low temperatures, we will sample likely items that are close to the decision boundary, and therefore they have high gradient magnitudes, but we have low confidence in the labeling, like we don't know if they are positive or negative. And on the other hand, with high temperatures, we will sample points that are far away from the decision boundary. They will therefore have low gradient magnitudes, but we will have high confidence in the labeling. So we have to find this trade-off. And along with this new sampling scheme, we define the Relaxed Softmax loss that replaces the normalization constant in the softmax function with one computed over a subset of items that are sampled from our sampling distribution BI. So K here is the number of negative items. And actually, so we were saying that it was over-parameterizing. Why? Because there is a special case where T equals infinity and QI is just the uniform sampling distribution, where we can reconstruct and approximate actually the softmax gradient. But we can see here that we can play with many different temperature parameters T and many different QI, and therefore this is how we will manage to have better performances. So now just a few examples to see the importance of the parameter T. So on the left we can see, so the blue continuous line in the background is the true distribution. The red dots are the sampled items, and the blue crosses is the estimated likelihoods. And what we see is, in both cases, we end up with a poor estimation because we don't manage to sample good negative items. Either we sample them like they are overly likely on the left, and on the right, they are too uninformative, too far from the decision boundary. So this leads to this small graph where we see the existence of an optimal temperature parameter theta star. This temperature parameter theta star will be problem dependent, and actually we have no closed form to solve it, so we consider it as a hyperparameter that has to be cross-validated. Okay. And now this, to validate the performances of our model, we ran experiments on language datasets and also recommendation datasets. We defined two simple models called popularity Boltzmann sampling and uniform Boltzmann sampling, where the degeneracy distributions are either popularity-based or uniform-based. So it's really simple models. And we play with the temperature, and we look at the performances. And what we can see is first, so both our models, UBS and PBS, perform a bit better. And actually, the interesting thing is we can see that the optimal temperature changes with the problem, and the more the problem focuses on the top of the distribution, for example, precision at 5, precision 15, it requires lower temperatures, because these problems will require harder negatives, closer to positive data, and that is why we have to go to smaller temperatures. And we can also talk a bit about the future works. It could be really interesting to see the efficiency of this negative sampling scheme on models with bigger capacities, such as convolutional neural networks or recurrent neural networks. It could also be interesting, the only QI we played with so far were uniform sampling or popularity-based sampling, and it makes sense now to use more interesting QI, such as the output of a first trained model. So yes, and also it could be really interesting to have a dynamical temperature that would change throughout training. So far our temperature T was kept the same and fixed during the training, and it would make sense to have dynamical temperature.